First of all, thank you very much for the kind invitation and introduction. I'm really pleased to give this talk in the mecca of geopolymer research. So title of my talk is Nanoaggregates synthesis from low temperature geopolymerization process for sustainability applications. So there are some keywords. So geopolymerization process, you know what geopolymerization means. Nanoaggregates are basically the aggregates or clusters made up of nanoparticles. So we make the geopolymeric or aluminosilicate nanoaggregates by using this low temperature geopolymer process. Of course, there has to be a purpose. We are mainly interested in using any kind of materials, any new materials, functional materials, for sustainability-related applications. So if we think about sustainability, human sustainability problems, so we are actually talking about energy problem, water, food, public health, global warming, environmental contamination. So all these problems are actually the problems of scale. So I throw in some numbers here. So there are about 8 billion people right now. It will be 12 billion people by 2100. We consumed 4 trillion cubic meters of fresh water consumed in 2014. And we are talking about a quadrillion BTU of energy that we are using. 33 billion tons of energy-related CO2 emissions. So these are all huge numbers. So if we want to really solve this kind of large-scale problems, we need functional materials, but we need functional materials that can be produced in very large scale. And geopolymer is one of those very few inorganic material systems that can be produced in large scale. That's why we became interested in geopolymer technology. So this slide shows some the large scale, some prominent large scale applications of geopolymer, pyramid stones, and the buildings by ancient Egyptians and Romans. And now we make the concretes and bricks and tiles based on geopolymer technology. So these are all large-scale applications. But then another thing that you realize is that even ancient people could use geopolymer technology. And the people in the field, they can produce geopolymer as long as they know the formula, they know the process. So the geopolymer process is actually fairly easy process. I mean, to chemists, this is actually fairly easy process to do. And easy process is very important in producing materials in large scale, and chemicals in large scale. So this is a quote by Sir John Conforth, a Nobel laureate in organic chemistry. So what he said was the ideal chemical process is that which a one-armed operator can perform by pouring the reactants into a bathtub and collecting the pure product from the drain hole. So it's this kind of easy process that's appreciated in industry, because if we have this kind of process if we start with a complicated the chemical process in the lab, it only become more and more complicated in industry. So we have to start with we have to find a very simple system that's very forgiving, and it can be eventually used in producing materials in large scale. And again, geopolymer or geopolymerization is one of those processes. So everybody knows this. So we start with metakaolin. We produce metakaolin, and then we add this into. We dissolve this in the mixture of potassium hydroxide or sodium hydroxide, potassium silicate, sodium sodium silicate, to generate a geopolymer resin, and then we cure this geopolymer resin at room temperature or above room temperature. Important, the keyword here is micro-sized microparticles. We are using microparticles of metakaolin. We dissolve this. This is a chemical process, and there will be the polycondensation. So polycondensation of this aluminosilicate materials are the dissolved species to form geopolymer network structure. Well, we start with micron-sized particles, but what we end up getting is nanostructure already. So geopolymer is innately nano. It has the nanostructure already. So this is the SEM image, and this is TM image reported by Professor Trudy Crippen. As far as I know, she's the first one who discovered this the nanostructured feature of a geopolymerization. So what you appreciate in this TM image is so we have this kind of some sort of particles that are strongly fused together to form very dense gel structure. So this is basically dense dried gel, dense zero gel. Like a structure. So this gel is different from what Professor Davidovich said. This is the typical gel network structure that the silica material has, or the metal oxide gel materials have. So what we have is already nano. So, but the problem is when we look at let's say the surface area of this material, that's about 10 to 20 square meters per gram. And with this kind of small particles, 10 to 30 nanometer particle size, you expect about 100 square meters per gram of that surface area. So what it means is all this the surface of this nanoparticles, most of this surface is not really accessible by chemicals or gas molecules that are coming in. So important thing is, well, let's open up this network structure further to make this structure really nano. And we use this nanostructure feature for certain functions, especially sustainability-related functions. So another way of looking at this idea is, well, compare this geopolymer with some other very well-known large-scale inorganic nanomaterials. So we have amorphous silica, so silica gel, sol, and precipitated silica. Precipitated silica is basically silica nanoaggregates. These are used in large scale. So 3 million tons of silica will be produced this year. So the industry, this is a $7 billion industry. There are lots of important applications. And the synthetic zeolites. Zeolites are also the nanomaterials. If you consider the micropores in zeolites, 1.3 tons, billion tons in 2008, and $9 billion business. Lots of applications. Nanoclay. This is relatively small, but then this market is growing fast. This is nothing more than the clay materials that have the organic surfactants on the surface. So this can be used as a reinforcing fillers, and so on. This amorphous aluminosilicate, well, this is different from geopolymer. This is produced through acid-base reactions. So the sodium silicate and the aluminum sulfate, you mix them together. But what you end up getting is not really geopolymer like a tetrahedral aluminosilicate network structure, but more like the 1/3 silica, 1/3 alumina, and 1/3 the geopolymer-like material. So this is something that that's problematic in terms of purity and in terms of the applications. So what I'm emphasizing here is geopolymer is very similar to all this. So it's aluminosilicate, tetrahedral network structure like zeolites, amorphous silica, tetrahedral network structure, clay, aluminosilicate with negative charges on the surface. So can we make geopolymer a lot? So make nanostructured geopolymer in large quantity and use this material for various applications. and basically provide the so-called platform technology like other materials do. So along this way, so we've been doing this for several years. We have been able to produce 3 different types of nanostructured aluminosilicates and 3 different types of synthetic methods. One is this meso macroporous geopolymer, Geopolymer Nanoaggregates, and nanostructured zeolites. So these nanostructured zeolites are basically zeolite nanoaggregates. So we consider this as nanoaggregates as well. But then it has highly crystalline geolytic the nanoparticles. So today I will just briefly talk about these 2. But I'm not going to talk about the applications, so the properties, so interesting properties that are directly applicable in larger scale. So before we start to talk about nanoaggregates, I want to describe the production of precipitated silica, because this is related to the production of a geopolymer nanoaggregates for comparison. So start with sodium silicate and sulfuric acid. This is nothing more than acid-base reaction. So when you mix this together, then what you end up getting is monomeric silicic acid. And this monomeric silicic acid is unstable in water, and it polymerized to make oligomers, and then these oligomers grow to make Sol particles, and these Sol particles grow and aggregate. So and eventually it will make a gel. But then if you do this very controlled stirring, then this gel break up into small clusters that are called silica nanoaggregates or precipitated silica. So this is basically the particle, the size of nanoaggregates, and this is the size of these primary particles. So this the production of precipitated silica is a so-called bottom-up process. So we start with molecular precursors, sodium silicate and acid. Or this is organic, the organosilane. So you basically start with these molecular precursors, and then you make Sol particles, and then you make nanoaggregates or gel. So that's bottom-up synthetic process. But what we are doing with geopolymer is we'll start with the clay, the metakaolin, micro-sized particles, microparticles. We break this up chemically. We dissolve this, and then we generate gel, or hopefully nanoaggregates, and eventually salt. So can we actually do this backward? This is a so-called top-down process. If we can do this effectively with the geopolymer, then we should be able to generate materials or various useful materials in an efficient way. So when I say efficient way, well, consider this a bottom-up process. So these molecular precursors, well, you cannot get them from the nature directly. You have to make this. So you have to give energy to generate all these molecular precursors, and then you go back to generate solids. So it requires basically a large amount of energy. But if we start with these micron-sized particles, metakaolin clay, and in the final geopolymer material, about 60% of the material, the geopolymer, actually comes from the metakaolin. So if we can do this effectively, then that saves lots of the energy and also the materials cost. And another important thing is this geopolymer process start with a very highly concentrated precursor solutions compared to typical the bottom-up process. So if we can do this right, then we can say we can produce the materials in very high, from 10 to 1,000 times more by volume. So if we have a container and you generate the certain amount of product. So if this is 1,000 times efficient, then the container size can be just 1,000th of the container that's That's for bottom-up process. So how do we do it for nano aggregates? Going back to this, the TM image as inspiration. So we just want to open up this structure, and then we want to break up this network structure. Then what we do is, well, just add more sodium hydroxide or potassium hydroxide. So that generates more the hydroxide terminated surface. And also, we add more water. So that provides more void, basically. So it's that simple. So we want to keep it simple. We do not want to modify. We do not want to modify the geopolymerization process. Just use exact the same process. You just add more the alkali and more water. So that's how we came up with this the nano aggregates. So synthetic exploration. So once we have this idea, then we want to basically find the right precursor compositions and the temperature and reaction time that gives the right the product. So I'm not going to talk about all these things, but bottom line is we have a systematic way of exploring the synthesis and well, basically and find out the relationship between the precursor composition, well, synthetic conditions and product properties. So under certain conditions, then we can generate. This is now potassium geopolymer. So under certain conditions, we can generate potassium-based geopolymer nanoaggregates. These are just schematic pictures. This is SEM and TM images. So in these SEM images, you see lots of particles that are actually agglomerates of this aggregate. So nanoaggregates are agglomerated together in this SEM image. And if we look at this individual nanoaggregate, this is the individual one nanoaggregate. That's about 100 to 500 nanometer size. This is comparable to silica, the precipitated silica. And primary particle size is 10 to 30 nanometers. This one shows the zeta potential. What it means is at this pH condition, the surface is highly negatively charged, so that this can be stabilized in water. That's actually desirable for lots of the applications in processing. And when we looked at the particle size distribution by using dynamic light scattering, the measurement, what we see is the particle size distribution is from 100 to 500 nanometers, and it's actually fairly stable. Again, we can make it a lot and very easily. So what we do is, well, so we make a right geopolymer resin with the right composition, put it in a bucket, and then close it tight, so we don't want to lose water during the synthesis. And then put it in the oven at 60 degrees C or 90 degrees C, take it out, and wash. And we get what we want. The production yield is very high, so 1 kilogram of material per liter of the precursor solution. This is just amazing. Nobody can get this kind of the high production yield for any kind of nanomaterials. So geopolymer is very unique. So then, well, as a chemist, I'm very much interested in how materials actually formed. So what we did was, well, instead of just looking at the product, let's just quench the reaction at the beginning and see what kind of material we have. So we start with geopolymer resin and heat this just for 30 minutes. And then we take it out and we add a large amount of water, but still the pH is very high so that the silicate doesn't precipitate out. So what we have is the aluminosilicate product that we collect, and we look at it on the microscope. So this is the TM image. So what you see is basically the geopolymer-like material here, and this is the partly dissolved metakaolin. So metakaolin is here, and then we have this new material. You zoom this in here, and what you end up seeing is well, gel-like structure look at it more closely, so this is now 20 nanometer scale bar. This particle, primary particle size is about 5 to 10 nanometers, much smaller than what you expect from the geopolymer final product. So this is what we concluded. When geopolymer, when the metacolumns start to dissolve, what we end up getting is salt-like particles. This has been already reported through SACS results before. So this is consistent with ours, but then this becomes quickly aggregate to form so-called primary geopolymer gel, where the particles, individual particles, are much smaller. And then, as time goes by, this grows. There is basically so-called aggregative growth of this to form a final geopolymer natural structure, or then aggregate, where we have a bigger primary particle size compared to what we see in this primary geopolymer gel. So what's the interesting thing about geopolymer is we always end up getting this kind of a structure with 20 to 30 nanometer primary particle size. We never go to this big, very dense geopolymer material. And this actually can be understood based on silica chemistry that people already reported. Even in silica synthesis, if you want to make very large particles, then let's say micron-sized the big particles, there should be no salt. So, but then geopolymer has lots of salt, sodium hydroxide basically, that limits the growth of geopolymer into very big particles. So that's with potassium geopolymer. How about sodium geopolymer? So we again we did a very systematic synthetic exploration for sodium geopolymer. So instead of getting amorphous the geopolymer nanoaggregate like in sodium the potassium case, we can get amorphous aggregate, and we can get all kinds of zeolite aggregates as well. So this is basically the TM images. This is potassium geopolymer nanoaggregates, and where the sodium we get something like this, and we get something like this. But then crystallinity is relatively low. We want to get 100% crystallinity because that kind of high high crystallinity is important for the geopolymer applications. Compared to the commercial micron-sized zeolites, this is now 5 microns. You can see that our nano zeolite aggregates are much smaller. So I'm not talking about applications, but then this kind of material has very large implication of very large scale applications. And we are trying to commercialize this product for certain applications right at the moment. We are actually building a large-scale factory at the moment to produce these materials. We figured out, now we move to the zeolite nanoaggregates, or nanostructured zeolites. So as I said, the crystallinity of zeolite from this process is relatively poor, but we figured out how to improve the crystallinity to 100%. So the idea is simple. We just add the vegetable oil at the beginning. So it's vegetable oil becomes the soap, and that reduces the alkalinity during this synthesis, the zeolite formation production process, and that reduces, that improves crystallinity. So this is gas option isosome. This is pore-size distribution. I'm not going to go through the details of this, but then this additional absorption of nitrogen gas indicates that this material has the additional big pores. And this is the initial uptake of nitrogen indicates the presence of micropores. So same amount of uptake for our material and commercial material means the crystallinity are very much comparable. Commercial zeolite particles, again, about 2 micron size, very big particles. This is 2 micron size, 2 micron scale bar here. This is our material. You can see that particles are much smaller, aggregate sizes are much smaller. We zoom this in. This is SEM imaging. So this is the aggregate size. We zoom this in further with the TM. So this is one aggregate. You can appreciate this is very highly crystalline, the shaped zeolite particles. Zoom this in further. You see this all these nice lattice fringes, all the way from the inside to outside. That indicates excellent the crystallinity. This you cannot get this kind of highly crystalline nanostructured zeolite by using any other zeolite synthetic methods. Only geopolymerization method can do that. So that's just amazing. So we zoom this in further, then actually we can even see the electron density map, and we can match it with the actual crystal structure. Again, we can make a lot. So this is just one batch, one-day experiment. I didn't talk about the applications of this, but then we found that with this kind of a nanostructure, highly crystalline and nanostructure, this kind of zeolite can perform much better, very, very well in the ion exchange process, antibacterial the applications, and CO2 separation. So as you know, the global warming, the carbon dioxide is one of the culprits, one of the most important culprits in global warming. And our material can remove carbon dioxide from the coal power plant or biomass very effectively, much better than commercial zeolite. And actually, it's one of the best materials. But then the important thing is our material is the cheapest. The cost of this production cost of this material is pretty much the same as the cost for conventional zeolite production. So with that, the take-home message is basically geopolymer process can produce aluminosilicate nanomaterials, including nanoaggregates, easily, inexpensively, in a scaled manner. I didn't tell you the detail about the sustainability actual applications, but geopolymer nanomaterials can perform very well in the sustainability applications. And geopolymer technology can be a platform materials technology for various chemical industries. And thank you very much for your attention.